As with all functions, the inverse of a trigonometric function is the result of switching the input and output. We learned that in Unit 2. Inverse functions switch the x and the y values. As a result, the output value of an inverse trigonometric function will be an angle measurement. So this is very important to know what I'm asking for in a trig question now, because I may not be asking you like one of these cards, tangent of pi. I may be asking you inverse tangent of 0. And your job is to give me back the angle measurement that would give you that trig ratio. We represent inverse trigonometric functions in two different ways. So your first option here for the way to, and the one I use the most, is inverse sine. So it's sine with a little exponent of -1. It's pronounced inverse sine. Notice that the -1 is not behind the x or behind the parentheses. It is behind the sin, pronounced inverse sine. The second option, and I don't particularly use this one as much, but it is very common in questions and in textbooks, is calling it arc sine. Those are literally the same thing. Inverse sine and arc sines are just two ways to write it. I think it had to do with like not being able to do actual exponents in old like computer print typing. So we made a new notation, which was arc sine, and then we got better at computing and could put a, like an actual exponent. So then inverse sine is there. Either notation, we say arc sine of x or inverse sine when reading it out loud. Now this little box is very, very important. What we did before today is we always plugged in an angle measurement, sine of pi, and we got out a trig value, some function value. But when we are doing inverse trig, we switch those input and output values. So for inverse trig, I'm going to plug in a function value, inverse sine of 0, and I'm going to get out an angle measurement, 0 radians. So we are switching the way we've done the quiz trade cards up till now, because these quiz trade cards had an angle measurement as the input and a trig ratio as the output, and now we're going to work backwards. So you do still have to know all of the values of your unit circles so you can work backwards. So we're going to write the statement sine of pi over 6 equal to 1/2 in an equivalent form using arc sine notation. Now again, pi over 6 is my angle and 1/2 is the trig ratio. That's the y over the r. But if we use arc sine notation, we would just switch all of this. We would say that the arc sine of 1/2 is going to be equal to pi over 6. That is an equivalent expression just written in its inverse form. You also could, just because I know that this is my habit to, instead of writing arc sine, to write it with the inverse symbol, you could also write it like this. Inverse sine of 1/2 is equal to pi over 6. Mathematician's choice really on that one. So we see we just switched the x's and y's. Switch the angle measurements with the trig ratio. Boom. And it's that easy. Part of your job today is to, without really using your unit circle, start to answer questions that would give you a blank here. So I could ask you arc sine of 1/2, and you'd have to be able to tell me pi over 6. So you're doing the unit circle inversely. But of course, there are some restrictions to trigonometric functions. They have to be functions. What's the one rule when in algebra 1, when you learned about a function, there was a major rule you learned about inputs for a function?
They can't be the same.
They can't what?
Be the same.
They can't be the same. You cannot repeat your input values. It had to pass what was called the
Straight line test. No.
vertical line test. So what we're going to do is we're going to invert that. Since we are doing an inverse function, we're going to do the horizontal line test. So vertical line test was for functions. Horizontal line test will tell me if a function has an inverse. So don't write this down, just watch. If I do the horizontal line test right now to this sine graph, does it pass the horizontal line test? No, it's how we have a problem here. But I'm telling you it's possible for us to have a function. So how is that going to be possible? What if we just chop off part of the graph? Okay, so what if instead of doing the entire vertical line test, what if I just start it here and I end it here? Does that pass the horizontal line test? Yeah, so what I'm going to do, and you can write this part down now, is I'm only going to highlight the section from negative pi over 2 to pi over 2. That is the only portion of the sine graph where we're going to define inverse sine. We have to restrict our domain. In order to make a function an inverse, we will restrict the function over the domain negative pi over 2 to pi over 2, as now we've highlighted it on the left. Yes, yeah. Same concept now for cosine. I have a cosine graph there for you. Okay. If I were to do the horizontal line test to see if its inverse would have a function, does it pass? No. So we need to also restrict its domain to make that happen. Don't write this down. If I do the same domain we did a second ago, so from negative pi over 2 to pi over 2, does it pass the horizontal line test? Oh, so we've got to switch what we're doing here. Instead of going from negative pi over 2 to pi over 2, what if I only went from 0 to pi? See that tiny little bolded section there? Let's highlight that. That is going to be the section where the inverse cosine function is defined from 0 to pi, because that's the section that will have no repeated y values, so we will have an inverse function that's a function.
So if we're given a function that doesn't have a restriction, then it's not a function?
It depends on what I'm asking you. If I say, does the cosine function with no restriction have an inverse function, you'd say no, because it does not pass. It has multiple input values for every unique output value, right? No, probably not. Because we know that to do inverse trig, we do have to restrict the domain. So it's well understood that when we're doing inverse, we're on this restricted domain. And then here's the tangent graph that you learned about last time. Again, if I do tangent, there's all the way across. Does it pass the horizontal line test? No, but this one's a little bit like, it looks like if you just take like one of those little S's, right? One of the little curves, we might be okay. So if we just look at this graph from the vertical asymptote to vertical asymptote here, from negative pi over 2 to pi over 2, that would pass the horizontal line test. Its inverse would be a function. Now notice that the domain that we're restricting it to this time, I changed to parentheses instead of brackets. Why do you think I'm using parentheses instead of brackets? Because it can't touch the asymptotes very good, so we're using parentheses at our endpoints instead of brackets. So the question becomes, what does this actually mean? And what does it mean for me when I'm doing some inverse trigonometric questions? And that is summarized on the back of your paper. Go ahead and flip it over. It is important to always remember and consider these domain restrictions when working with inverse trigonometric functions and values, specifically on a unit circle. Remember, for sine, we said that we could go from negative pi over 2 to pi over 2. Negative is clockwise. So if I started at 0 and went negative pi over 2, it's like 90 degrees, yes, in this quadrant. So we're only going to define inverse sine functions in quadrant 1 and quadrant 4. So if you have a positive input value, you're going to give me an angle between 0 and pi over 2. If you have a negative input value, you're going to give me some angle between negative pi over 2 and 0. Okay, that's pink. Since cosine was restricted on a different domain, we were restricting that one from 0 to pi. This one looks kind of normal to us because we start at 0 and we go all the way to pi. This is 0, this is pi. Those are the two quadrants where cosine has an inverse function. These are the angles you will give back to me for inverse cosine. If I ask you for a positive input value, you would give me an angle between 0 and pi over 2. If there is a negative input value, you would give me an angle between pi over 2 and pi. For tangent, we define tangent in the fourth and the first quadrant, which was from negative pi over 2 to pi over 2. And just like sine, if the input value is positive, that tangent angle will be between 0 and pi over 2. And if you have a negative input value, the angle that gives you that negative input value would be between negative pi over 2 and 0. So which quadrant should you never give me an angle for? The third. Do any of these go into the third quadrant? No, you should never return to me an angle that is larger than pi and smaller than 3 pi over 2. We don't go into that quadrant for inverse trig. A lot of them are going to come out of quadrant 1 because that's where all the positive values are. You have to work backwards when it's sine and tangent, which actually is somehow easier. And then cosine, you can go into the second quadrant, so you're going to have those more obtuse angles. Okay? Let me show you how we're going to do this. You can't go all the way around the unit circle for sine and tangent, which actually makes it somewhat easier. If we're evaluating the following, inverse cosine of negative square root 2 over 2. First of all, the input value is negative, and this is a trig ratio, which means you're returning to me an angle. It's negative, so which quadrant should this one be in? 2. Now, square root 2 over 2. Think about the hand trick. What angle would give you square root 2 over 2 for cosine?
4.
Pi over 4, yes? But if we're in the second quadrant, what version of pi over 4 is that? 3 pi over 4. The inverse cosine of negative square root 2 over 2 is 3 pi over 4. We just did the unit circle inversely. What? Cool.
No, don't ask me anything.
How about inverse sine of negative square root 3 over 2? First of all, it's negative, so which quadrant should we be in? For sine? 4. But remember, we're not going to go all the way around the unit circle. We're just going to go negatively. So let's think about it. What angle typically gives you square root 3 over 2 for sine?
Square root 3. Pi over 3.
Pi over 3. But we want it to be in quadrant 4, except we're not going around the circle, so look how easy this is. This is just negative pi over 3. You told me pi over 3, but we know it's negative, so it's negative pi over 3. That does get me in the fourth quadrant, but I didn't go around the unit circle because I can't go through quadrant 3.
So now we're allowed to go
Backwards.
counterclockwise?
Counterclockwise is normal. That's a positive angle. Clockwise, yes, is a negative angle. You've always been allowed to. I just haven't done it very much. But yes.
Because we're thinking in measurement almost, right? Where it's you can't go never mind.
I understand what you're
It's
saying.
just never mind.
Okay, I didn't follow that at all. I will not lie to you.
Just a way. It's because we're just a little slow.
It's fine. We're learning. Okay, what about inverse tangent of square root 3? First of all, that input value is a positive trig ratio. What quadrant are we in? 1. Anytime it's positive, we're in quadrant 1. These are the easies. What angle would give you square root 3 when you take the tangent of that angle?
Or pi over 3.
So inverse tangent of square root 3 is pi over 3. We're just doing our unit circle backwards.
Did you hear what I said?
I did not, if you're talking to me.
Pi root.
Listen, it's a Monday. How do we feel about these 3? Example 2. That's going to be the majority of what I ask you to do today with our inverse trig, because for the most part, where this comes in handy is going to be FRQ4, where you just need to know these values without a calculator. So just knowing your unit circle and knowing the inverse of the unit circle is huge. Okay? Example 3. It says angle theta is in standard position. First of all, just find angle theta, because I've realized throughout the test we just took, we're struggling to find our angles. Actually, look at the document and the image. It's going to show you theta. What quadrant is theta in?
1.
Fabulous. The terminal ray intersects the unit circle at point P, whose coordinates are x, y. The points Q, R, and S are the results of the terminal ray being reflected over the y-axis, the origin, and the x-axis, respectively. For each of the following expressions, determine which labeled point intersects the terminal ray of the given angles. If we were finding the inverse cosine of x, first of all, cosine is which coordinate point around a unit circle? X. So I want the inverse cosine of x. What point is that? Yeah, let me back up because I feel like I'm doing too much in my head without thinking about it. Let's go back for a second and let's write the coordinate points of Q, R, and S on our paper. What is the coordinate point of Q?
R.
I mean, r cosine theta, r sine of theta. But if this is P, negative x comma y. There we go. Now we're cooking. All right. What is the coordinate point of R? And then the coordinate point of S? Okay, so we have all these coordinate points. So we have the sine and cosine value of all of these coordinate points around the unit circle. What point would give me cosine inverse cosine, sorry, of x? So my question becomes, where is there an x term? Oh, but this one is negative x. This one's negative x. What about just regular x? P and S. Now, if I'm doing inverse cosine, am I allowed to use this coordinate point? No. Cosine is only allowed to be in which two quadrants? 1 and 2. So the coordinate point that would give that to me is P. I made that very confusing, so sorry, everybody. What about the inverse sine of negative y? Okay, where are the negative y's? 3 and 4. Which one should you use for inverse sine? 4, which means this would be coordinate point S. Can we ever use 3? No. Okay, great. How about the inverse cosine of negative x? Which coordinate point would I use? Q. Do we see why? We can't use 3. But inverse cosine being the first coordinate, would be negative x here. How about inverse tangent of negative y over x? Ooh. I actually heard the correct answer. This would be S. Why is it S? Can't use 3. And can you use 2 for tangent? No, you can only use 1 and 4. So the only way to make this negative, yes, is if it's out of this quadrant for inverse tangent. Interesting, interesting. So the point of today is to get you used to now looking at your unit circle inversely. So just like we had a GIM kit to practice our regular unit circle, I also have a GIM kit. This one is not a grade. Everybody breathe. We're going to practice inverse trig on a GIM kit.